The same material that refuses to burn in bulk form becomes a fountain of fire when restructured into countless thin strands. It's a perfect illustration of how material properties shift dramatically based on physical structure. The next time you see steel wool in a store, remember there's genuine chemistry and physics hidden inside that seemingly ordinary pad. Manufacturing processes have transformed solid steel into a form with extraordinary surface area, creating conditions where oxidation becomes explosive and visible. It's a reminder that even the most common household products have fascinating science behind them. Thank you for exploring the science of steel wool with us. Subscribe for more discoveries hidden in everyday items, and let us know what topics you'd like us to investigate next. Stay tuned for more stories woven through the smallest details. As iron atoms combine with oxygen molecules, they release energy in the form of heat and light. This reaction becomes self-sustaining once it starts. The heat generated by the burning fibers ignites neighboring fibers, creating a cascade effect. What you witness is a rapid chain reaction spreading across the entire bundle, producing that spectacular shower of sparks. The visual effect is particularly dramatic because as steel wool burns, tiny fragments of heated metal are ejected from the burning fibers. These particles shoot through the air while remaining extremely hot, continuing to react with oxygen as they travel. The glowing fragments create streaks of light, those characteristic sparks that genuinely resemble fireworks displays. The effect is so visually striking that photographers have adopted it as an artistic technique. By placing burning steel wool inside a metal whisk attached to a chain and spinning it, they can create enormous glowing circles that look almost otherworldly. Each individual spark you see represents a fragment of iron releasing tremendous energy as it oxidizes. The spectacular light show is essentially millions of tiny oxidation reactions happening simultaneously and continuously. So why such a difference between burning steel wool and solid steel? The answer returns to surface area. In solid steel, most atoms are protected inside the material. Oxygen can only interact with the outer surface. That limited contact means slow oxidation. Steel wool, however, exposes iron atoms from every direction. The fibers are so thin that nearly every atom has potential contact with oxygen. This exponentially increases the reaction rate. This principle extends far beyond steel wool. It's why flour can ignite explosively in the right conditions despite being made from grain that certainly won't burn normally. It's why fine metal powders are treated carefully in industries because they present explosion hazards. It's why campfire tinder works. Thin, dry material with high surface area catches and spreads fire far more easily than solid wood. Surface area determines reactivity. Creating steel wool is an elegant manufacturing process. It begins with steel wire rods, thick cylinders of metal. These rods are drawn through a series of progressively smaller dies, gradually reducing their diameter to create long, thin wires of precise dimensions. But the actual transformation happens in specialized shaving machines. Rather than cutting the wire into pieces, these machines shave incredibly thin ribbons directly from the wire's surface. Think of it like peeling a long, continuous strip from a block of wood with a knife, except happening at microscopic scale with absolute precision. As the machine shaves the steel, thousands of delicate strands curl and twist naturally as they're produced. This curling creates the distinctive, fluffy, tangled texture you recognize as steel wool. Once generated, these fibers are collected, cleaned, and sorted by thickness. Manufacturers grade the finished material using numbers that indicate coarseness. Higher numbers mean finer, more delicate fibers. Finally, the steel wool is compressed into the pads and rolls you see in stores, then shipped to consumers and professionals worldwide. What appears to be a simple household product actually requires sophisticated machinery and engineering to produce at scale. Now we can address the central mystery: why does steel wool burn so dramatically? In its conventional form, solid steel is remarkably difficult to ignite. A steel beam or a thick steel plate exposed to flame won't suddenly catch fire. Most of the steel's atoms are buried deep inside the material, protected from oxygen in the air. Without sufficient contact between those iron atoms and atmospheric oxygen, combustion happens extremely slowly, barely perceptible. A steel pan on a stove doesn't catch fire, and steel frame buildings don't burn like wooden ones. The metal's density works against rapid burning. Steel wool, however, presents a completely different scenario. The secret is surface area. Each strand of steel wool is microscopically thin. When thousands of these strands are jumbled together into a pad, they create an enormous exposed surface compared to a solid piece of steel of identical weight. This means vastly more iron atoms have direct contact with oxygen molecules floating in the air. When you introduce sufficient heat to steel wool, whether from a match, lighter, or battery, the iron atoms begin reacting with oxygen far more rapidly than they could in solid steel. Technically, this is oxidation, the same chemical process responsible for rust formation. But there's a critical difference in speed. Rust develops over months or years. The oxidation happening in burning steel wool occurs almost instantaneously. You're standing in a workshop holding a simple pad of steel wool. To most people, it's just another cleaning tool, something you use to scrub away rust, polish metal, or prepare surfaces for refinishing. Ordinary, unremarkable. But if you touch that same pad to a battery or expose it to a flame, something extraordinary happens. Suddenly, the steel wool erupts into a brilliant cascade of sparks and light, burning with an intensity that resembles a fireworks display. It's a transformation so dramatic that it seems almost magical. The puzzle is obvious. Steel wool is made of steel. Steel is the material we use to construct bridges, skyscrapers, and ships. Structures built specifically because steel resists fire and extreme conditions. So how is it possible that steel wool burns so ferociously when solid steel barely reacts to flame? The answer lies in one of the most fundamental concepts in chemistry: surface area. And understanding this reveals something remarkable about materials and how their behavior changes at different scales. Let's start with what steel wool actually is. Despite its name, it contains no wool whatsoever. Instead, it's a bundle of incredibly thin metal strands. Thousands of them tangled together into a loose, fluffy mass. Each individual fiber is made from low-carbon steel. But what's crucial is how thin these fibers are. They're so delicate that you can easily bend them with your fingers, compress the entire pad into a tight ball, or stretch it out without any resistance. Steel wool isn't a single product. Manufacturers produce different grades, ranging from very coarse to exceptionally fine. The coarse varieties are designed for heavy-duty work, like stripping paint or removing serious rust. The finer grades are used for more delicate tasks, polishing wood, cleaning glass, or achieving smooth finishes on furniture. Some grades are so fine they almost feel like fabric when you touch them carefully. But regardless of the grade, every type of steel wool shares the same critical property that makes it useful: an enormous amount of surface area concentrated in a small space. The history of steel wool is relatively recent. In earlier eras, people relied on sand, pumice stone, and natural scrubbing materials for cleaning and polishing. But as industrial manufacturing advanced during the 1800s, metal workers developed better techniques for creating thin metal fibers. By the early 20th century, specialized machinery could produce steel wool efficiently and at scale. Despite the invention of modern synthetic alternatives, steel wool remains popular worldwide because it's durable, effective, and inexpensive.